Okay. Any question about the previous session? Well, in the previous session, we generally talk about probability and statistics, and especially our notation. We talk about both discrete random variables, the continuous random variable, the concept of PMF, the concept of PDF. We see one well-known PDF, Gaussian, and this is our notation during this course. From the context of the random variable written here, you can understand where this distribution is defined on. It means that we do not have any subscript here, as you may see in your probability and statistics course, for the simplicity of notation, and you can see that it can share along all different types of generative modeling. Today, we want to continue our discussion about expectation, and we want to have the concept of expectation as the result of several experiments. So, assume again our previous example where you have a person and you want to see how many hours he can walk in 6 hours. This was our example about PDF. He can walk between 0 and maximum is 6 hours. So assume that another information is given to you that based on the time he walked, the energy consumed by this person can be calculated using this red curve. So you have this blue curve, you have this red curve. And as you can see, for any point, you can see that what is the probability of that point, and at the same time, what is the energy that the person consumes in that number of hours. Okay, but what is our approach for expectation? What is the definition we are looking for expectation? Is that in general case, expectation can be interpreted as the average for the function epsilon of x in a large number of independent, the independent term is very important here, repetitions of the experiment. It means that assume that you select that person for several times and observe him how many hours he can walk, then evaluate the corresponding epsilon of that hour, and then multiply this together, and then you have an energy. Repeat this experiment for several times such that your experiments are independent. It means that it is not valid that when he walks now, you cannot expect him to walk 1 hour later. Because the experiment should be independent, for example, another day he should start his next experiment because we want the independence. So the expectation is the mean value for several independent repetition of the experiment. And we denote the resulting value with this notation. This notation is very, very important during this course. We will see it for several times. What does it say? It says that start sampling this distribution and call those samples x. Lowercase. Why? Because it is a numeric value. You sample. It is not the random variable yet anymore. So then calculate the epsilon for that sampled value and then average these values of epsilon. This is the expectation of epsilon with respect to the distribution you see here, P of random variable x. This is our concept for expectation. You may see this definition before. So how can I calculate this concept? One approach is by sampling, and another approach is by probability density function. As you can see here, it means that you weight any point by its corresponding probability and sum the result over all valid numbers of x, we assume that x is extended from minus infinity to plus infinity. So this is the one approach to calculate expectation. Another one is based on independent repetitions. Similarly, for the case of discrete random variable, you can calculate your expectation using probability mass function. And as you can see, we do not have any difference between continuous and discrete random variables. So what are some well-known examples of expectation? Assume that if I select this f of x equal to x, the resulting expectation is called the mean value, and it is denoted by mu. If I use this function for f, means the deviation around the mean to the power of 2, the resulting expectation is the variance, and it is denoted by sigma to the power of 2. If you use the x to the power of n as your f function, then the resulting expectation is the nth raw moment. Raw moment is due to the, it is around 0, we call it raw moment. And it is denoted by mu subscript n superscript prime. So this is the definition of expectation. Aligned to the expectation, we have a very, very important estimation, which is Monte Carlo estimation. We use it in almost all of our methods. Monte Carlo estimation. What is the Monte Carlo estimation? Assume we have a random variable x, a random vector. It is written here. It is my mistake. It is a random vector because the notation showed that it is a vector. We have a random vector x with distribution p of x. The expectation of the function f of a vector, because you have a vector here, you have also a vector, can be calculated as this definition. This is the original definition of expectation. We do not have any point about this definition. So now assume that instead of p of x, you just have access to n independent samples of the random variable and call them x1 to xn. What is this case? What this case remind you? This is the case of data set. Instead of the true data distribution, you have some samples from the true data distribution. And we can assume that those samples are independent. This is a logical assumption. So we are going to the point that we can calculate the expectation of a function using a limited, as you can see, it is not a large number, it is a limited number of experiments. So what does Monte Carlo estimation say? It says that define the Monte Carlo estimation as this. Simply, I made a mistake here. I should use f of x here. F of x. It is not xn, it is f of xn. Okay? Assume that I form this estimation. It means that for those, for the set of random variables I have, random vectors I have, I evaluate the f and then average them. This is the definition of the average over f of x. I made a mistake here. This is the Monte Carlo estimation. It is not very well understood here that how it can be used for the estimation. But using the weak law of large numbers, you can show that this limit will become 0 if you increase your number of samples. What does it say? It said that if you increase your independent samples, as you increase your independent samples for arbitrary small positive epsilon, you can make this probability equal to 0. Or in other words, your Monte Carlo estimation is exactly equal to the expectation value. But what we do not use it in this case. We use it in a limited number of n, which is, for example, this large n, this uppercase n, and we can show that it can estimate the true expectation. Assume that I have a random variable, a Gaussian random variable, with mean 1 and variance equal to 4, we know that the expectation of this function is equal to the variance of the distribution, which is 4. This is easily understood from the definition of variance. But assume that I use independent samples from the distribution to calculate this expectation using Monte Carlo estimation. In this curve, you see that the red curve is the true value of the expectation, and the blue curve is my estimate using Monte Carlo estimation. As you can see, for the small number of n, you have a high variance around your true value, but as you increase the number of n, it is a better estimation to the true expectation. So we want to work on these regions. Instead of having the true expectation, we just want to approximate the estimation in some places using the Monte Carlo estimation. And you know that in the case of our problem, we just access to data samples from the true distribution. You do not have any true distribution because you are estimating that distribution, and it can help you much in that case. Okay, any question about the expectation and Monte Carlo estimation? So, another topic that we want to talk about in this presentation is the distance metrics. We do not want to introduce all the distance metrics that we use during the course, but some of them that is used for several times during different generative models, we talk about them here. The first distance metric is the Kullback Leibler divergence, which is written as KLD. KLD is a metric to calculate the distance between two distributions. KLD for two distributions P and Q. Pay attention. You have a problem. You have a random variable x. You have, this is standard. What is this? Is a random variable with, for example, it is a categorical random variable. It has L categories, 1, 2, 3 to the C categories. Over this random variable, you can define different distributions. You have lots of distribution over this random variable. One of them is P, and the other is Q. You want to design a metric that can show the divergence between these two distributions. They are shared over one random variable. The random variable is not changed. So, the KLD is denoted by this notation and is defined as an expectation. It is the expectation of this value over the samples coming from the first distribution. What does it mean? It says that start sampling from your first distribution P of x, and then calculate this ratio between those samples. Each of these distributions assign a probability to that sample. Then take the logarithm and then average through independent samples you get from your distribution. This is the value of your KLD. In other words, you can calculate it for discrete random variables, as you can see here. But it has some properties that are very important for us. The first one is that KL is not symmetric. It is very easily understood that you are sampling from one of those distributions. So if you change them, you are sampling from the other one. And it is evident that they cannot be equal. Second is that the KL divergence is non-negative, so it is suitable as a divergence. It cannot be negative. The next one is that if two distributions are equal, then you see 0 in your KL divergence. It is very suitable. It is very great of a feature because you can understand that when your KLD is 0, you can make sure that the two distributions are similar. For example, we want to compare P of data and P of theta, the most important distribution we work with during this course. If I observe that the KLD between these distribution is 0, I can make sure that I ideally approximate the true distribution. Yeah. A bad property is that KLD is not upper bounded. It can be infinity plus infinity. And the last one is that the KLD cannot be a distance metric. Distance metric, it is a metric to calculate distance, but it is not a distance metric because distance metric has some specific properties. One of them is symmetric. It must be symmetric, but the KLD is not symmetric. Another important property that this distance metric has is that the distance metric satisfies the triangle inequality. What does it mean? The triangle assumes that I have three distributions over the random variable x. It means that the KL between for example, the first and the third should be less or equal than the KL between the first and second plus the distance between the second and third. It is not valid for KLD. So KLD is not a distance metric, but it is a great divergence for us. We can measure how similar are two distributions, and you can see that we use it in several places. So assume that I have a categorical distribution over one random variable with 6 different states. I have two distributions, P of x and Q of x. P of x is the red PMF, Q of x is the blue PMF. What should I do to calculate the KLD? First, I need the first distribution because the expectation is with respect to the first distribution, so I plot it here. And I needed this logarithm value, the logarithm of the ratio in each of the states of the random variable, and they are also plotted here. As you can see, in the places where they assign similar probability to the state, this log value is 0. It is a favorable. Why? Because when they are similar, the distance or the divergence is 0. When it is not, they are not equal, the divergence will increase. And as you can see, you weight the blue curves using the red curves, and then you sum them. This is the way you calculate the KLD. And you can see it here for the above two distributions. The result is 0.64. And it can be easily designed for the continuous random variables. Instead of the summation, you have the integral over the valid numbers for your random variable. Okay, one important point is that the JST is a smoother divergence in comparison to KLD. You can understand it from the being upper bounded. It cannot go to the infinity, so it seems that it can be smoother than KLD, and you can see it here. What is this curve? You have one distribution Bernoulli with parameter 0.4, and you have another distribution Q, which is a variable distribution based on its parameters. The result, this curve, this axis is the parameter for the Q, and this is the divergences, the KLD and the JST. As you can see, when the parameter is equal to 0.4, they are equal, so you have 0 divergence for both KLD and JST, and as it diverges from 0.4, your divergence increases, but the value for the KLD is, you can see, is more. The value for JST is more smooth than the KLD. So in some cases, you will find JST more plausible to use, but sometimes you cannot use it. As you can see, for example, in some cases of autoregressive model, KLD can only be used. Okay. So altogether, what do we see in this presentation, we talk about the notation, then we talk about the probability and statistics, we talk about the probability density and mass functions, we talk about expectation and about the distance metric, and this is the list of the abbreviations used during this presentation. So, any question about the foundation part? Yeah.
So since KL is not symmetric, like how do we figure out over which probability distribution we need to find the expectation, whether P or Q?
Yeah, you will see that if you change that, in some cases you cannot evaluate even KL. It is important that you are working on, for example, we are in the case of a generative model. You are working on KL between P of data and P of theta, or the reverse. You can see that this one is much more easier to evaluate, and the other one cannot be used because you need to sample from your generative model. But here you need to sample from your true data distribution. How we can sample from true data distribution? Sampling from the data set. Because data sets are independent samples from the true data distribution. So this one is easily calculated in the case of the generative model, but the other one is very, very hard because you need to sample from your model. In some cases, it is very hard to sample from the model. Yes?
So what are the characteristics of KLD and JST when you say have different properties in your distribution? So like, say we have like long tails or really narrow peaks, how does that affect?
Yeah, you know, KLD, because of the property that it can be infinity, in some cases where your first distribution assign probability, but your second one is 0, you have severe problems because the KLD become infinity, so it cannot be used. It is not the case for generative models, and you do not face this problem generally. But in the general case where you are working with distribution themselves, I mean that you are not sampling. You use the PDF, just the integral or the summation. In those cases, you may have problems with KLD, which are not the case for JST. About the tail, you mean that in the outliers case?
Yeah.
In the outlier case, maybe KLD, in the outlier case for the first distribution or the second, it is important because you are sampling from the first distribution. This is the distribution that you are sampling. If you are talking about the outlier of this distribution, it is important that are those samples outlier for the second two or not?
So the first distribution is your data set. So
just to have some intuition, maybe it's in some cases, for example, in GANs, you can see that they are working on JST instead of KL. It means that both this KL and the other one. It is dependent on the model.
So why not always use JST?
It means because, for example, assume sampling from the data distribution is very easy, you know. But assume that I want to calculate, I do not have access to the true data distribution, so I cannot use the formulation using summation or integral. Assume that I want to calculate this. Again, if I want to use the integral, because these generative models are very complex models, you cannot use the integral. So you again must use the sampling. But now you should sample from a model. And in some cases, sampling from model is very time consuming. For example, in energy-based models, sampling from the model is equal to solving an optimization problem to some extent, not to convergence. So in some cases, it is very difficult. Yeah. So we use the first one because it is easily equivalent to sampling from data set. You select some samples from the data set. Okay. Any question? We want to enter our first model. Okay. Okay, what is our first model? As you may remember in the first session of the course, I said that why we cannot use something like multinomial or binary logistic regression to have generative models. We see that, why they are not applicable there. But in this case, and the autoregressive models, we want to simplify, to have the modeling such that we can use those ideas here. You can see that how we change the model so that we can use multinomial logistic regression easily to have a generative model. It is more important. It is the important point is how you select your family, your P of theta, the family you select. We will talk about these four. These are the family selection part. As you remember, we have this concept. We have a total distributions. We select a family. The first four topics are related to how to select this family. Then we talk about how to learn. In the learning part, we both introduce the distance and also the optimization. So at the end of this part, you will be able to train a generative model using autoregressive model. And then the example and conditional and the applications and summary. So let's start with fully visible sigmoid belief networks and to see what are these networks. So assume that I have binary MNIST. Binary MNIST, what is the binary MNIST? The binary MNIST is a data set where your X are binary samples. You have seen the MNIST data set. MNIST data set is a data set of handwritten digits. In our case, we just have 0 or 1 pixels. So it is not a grayscale as it is in the original data set. It is 0 or 1. And you can also easily understand the context or the digit in the image using the binary image. So the X is from this dimension, X is 0 or 1 is sample and it is with this dimension, and Y, the label is one of these numbers. I want to change this data set. How? I want to design new labels, and this label is 0 if the true label is less than 5, and it is 1 otherwise. So I make them problem. I transfer the data set into a new data set where both the pixels and the labels are binary. Do you agree? Okay. So in this data set, assume that I want to estimate this new label using the input data. What can I do? I can easily use binary logistic regression. Why I can use binary? Because the labels are binary now. So by estimating just one parameter, which is the parameter for the Bernoulli distribution, I can solve the problem. So the resulting model for this problem is this conditional distribution. What it said? It said that you should define a distribution over 0 or 1 using the input and also some parameters of your model. And as you can see, the most general case here is the Bernoulli distribution. It is the total family. This is the full box. And I use an affine transformation over the input, and a bias affine transformation over the input and a sigmoid nonlinearity to generate the Bernoulli distribution parameter. This value, the input to the sigmoid can be any number between -infinity to +infinity, and as a result of the sigmoid, I have a number between 0 and 1, which is suitable as the parameter for the Bernoulli distribution. Okay. This is the classical problem you have previously seen. These are the definitions for the parameters. And the training is easily done using a different method you have previously seen, such as cross entropy or those types of losses. In PyTorch, you have different classes for this problem. But I want to start generative modeling using exactly this idea. How can I do that? Assume that now I have just access to BMNIS, binary MNIS images. We put the labels aside. We do not have the labels anymore. And we just have access to the binary data set, as you can see here. So I can define a distribution, the complete family. The complete family of distribution, the box, for this size of the random vector is can be factorized using chain rule. Any problem? Just a change of notation. I introduce this new notation, x subscript less than 2. It means that the samples, the elements in the input vector whose index is less than 2, and less than I means that the sample elements in the input whose index is less than I. This is defined here. This is, I do not impose any restriction till now. It is just chain rule, and chain rule is the complete family. So, but I have an idea here. Let's focus on one of these distributions. What do you see here? For example, this one. What is this problem? P of xi given vector, this is a vector, I emphasize with this underline, vector x less than I. What is this problem? You want to estimate a distribution over a binary random variable. It is a binary random variable. You agree? Because 1 pixel of the input image, given all the other elements before that element. So, given means that you have access to them. These are input to your distribution. How can I model a distribution over a binary random variable? With Bernoulli, exactly. So I can start from the beginning. The first one is simply a distribution without any input. So it can be estimated using a Bernoulli random variable with parameter b. I have sigmoid of b because of the notation of the other parts. You can see that. So I introduce one random variable here. Okay, no restriction yet. But I start to impose restrictions here. How? For the ith element, for the ith pixel, which is 0 or 1 again, I am given the vector of the previous ones and one vector and one bias scalar. And how I model the distribution, I said that the distribution over this index is a Bernoulli with this parameter, and you can see that why I use sigmoid here, because I want to have shared notation between different elements. So what happened here? I impose some restrictions. In the general case, what should I do here? Assume that I am in the second place and I want to model this distribution. How many parameters should I have here? For the general case, I should have 2 parameters. One for this distribution, the other for this distribution. So 1 parameter here, 1 parameter here, 2 parameters here. The next one, oh, sorry, I use Persian digits. How about here? How many parameters do I have to model in the full context here? How many? Exactly, 4. Because one time I write x1 and x2. 0, 0, 0, 1, 1, 0, 1, 1. For each of them, I have a Bernoulli random variable over x3. So I need a parameter. One parameter here, one parameter here, 4. In the I, which is written here, in the general case, how many parameters? 2 power I. Exactly. 2 power I minus 1. Because for the I, we have I minus 1 here. Am I right? Yeah, yes. 2 to the power I minus 1. But how many parameters do I have here? 1 here, and how is the dimension of this? I minus 1. So I decrease the number of parameters from 2 to the power of I minus 1 to I. This is the limitation that I impose. So I restrict from the complete set to a limited set by increasing the number of parameters. Okay? This is just a review of these numbers. In the general case, as we see before, for the P, calligraphic P, we know that the calligraphic P means this family, complete, and the P of the calligraphic P subscript theta means this, our family, our selected family. In the general case, I have 2 to the power of n minus 1 because you have no restriction. You have 2 to the power of n different states. So you have 2 to the power of n minus 1 because the summation should be 1. But here, for our case, that we start some limitations. The first one has just one parameter, which is B1. The second have 2 parameters, B2 and W2, because W2 is still an scalar, because x less than 2 is just one element. And the last one has n parameters. So totally you have n times n plus 1 over 2. So you drastically reduce the number of parameters from the model. And again, you use exactly binary logistic regression here. For each element, you have a binary logistic regression. Remember that in the previous session, maybe the first session, we see that one approach, one of you proposed to apply, for example, a binary logistic regression for each pixel. We again here have a binary logistic regression for each pixel, but what is the difference? The conditioning is on the other pixels. It means that the correlation, the relation between the pixels is completely working here because the parameter for each pixel is designed based on its previous pixels. The most challenging point is this topic, previous pixels. Previous pixels is not well defined, for example, in the context of image, because you do not know that how you can consider an order for an image pixels. You know, this is a challenging problem. How to consider an ordering, for example, in an image. For example, I consider this ordering and then start from here. I can consider raster scanning or any type of the ordering, but there are some signals or there are some inputs which have order in their nature, such as text, such as speech, such as audio. They are ordered in their nature. So they can be easily fit to this framework. Yes?
I'm slightly confused. You said that the vector, you said that Wi is a scalar, but if you're taking the dot product with x,
just this one is a scalar. After that, I mean that just I want to show that this notation is correct because it is not bold. It means that just the B2, the W2 is a scalar because it should be multiply with x vector less than 2, which is again a scalar. Both of them are scalars, but the next one, this is a vector. Why? Because this is first element, second element, it is transposed. We always consider the vectors to be column vectors, so this is a transpose of the column vector, and x less than 3, as you can see in the definition of here is x1 and x2. So the multiplication can be done, and just a bias term is also included. The notation is 3. This is the result. So you are using previous pixels or previous elements in your input vector to estimate the distribution over your current elements. And it is the way that you consider the correlation between different elements in the input vector.
So considering that, then can you do like parameter sharing, because the maximum W can be is like n?
Yeah, exactly. Here, because the number of parameters is very low, it is very small, we do not share the parameters. But for the next models, you can see that we can easily share the parameters, and then the performance is much better in the limited size of the data set. Yeah. Yes. But here, we generally for the case of the fully visible Sigmoid belief networks, you do not share the parameters. Yeah. Okay. Let's. So now assume that we are generating a subset of the true complete set of distributions, and I introduce a family here. If I assume that this is a complete set of family, I am limiting the family in the case you see here. I should be able to do two tasks. One of them is density estimation. The other is what are our main tasks in generative modeling?
Generation.
Exactly, generation. How can I density estimate or generate using this model? So for now, assume that all the parameters are given to you. We do not want to know how they are trained. We will see how they are trained at the end of this presentation. Assume that someone give you the whole set of parameters. It means that B2 till Bn, and I think not D, BD here for this data, because it is D-dimensional. And also the weight vectors, B2 till BD. Assume that you have access to all of them. And now someone give you a new vector, X, and ask you to estimate the density. Yes?
I think that the ink is quite...
What?
I'm unable to see what's written on the board because of the ink.
You mean you cannot see the board?
Yeah, because of the ink.
Oh, yeah, sure. I will change it. Assume that someone... It's better. Thank you. Assume someone give you a vector and ask you to give him the probability for that vector. It is a common task in generative model. For example, you want to see whether that input is an outlier or not. For example, for outlier detection. What do you do? Based on the model we see before. So I have an input. These are given to me. These are all known. These are our numeric values. What should I do? The first step is to see what is, remember our factorization. Our factorization said that the probability you want to evaluate is the multiplication of several conditional probabilities, yes? So, the first element, I mean that they are multiplied. The second element given the first until the last element given the previous ones. So I should just calculate these conditional probabilities and then multiply them together. This is the result. So the first one. This is the first one. We know that the first element have a distribution with this parameter. You should, this addition is for the next one. So it is B1, enter a sigmoid nonlinearity and generate the parameter for the distribution over x1. Remember that the distribution over x1 is Bernoulli. I write the distribution, let's see here, is Bernoulli with this parameter sigma over B1. We see it before in the previous slide. So I just need to calculate this value, which I call here lambda 1. Here, I call it here lambda 1. B, enter a sigmoid, this is lambda 1. Oh, okay. What is the probability for your first element? You should check. If your first element is a 1, it means that its probability is lambda 1. Why? This is a Bernoulli with parameter lambda 1. Lambda 1 indicates the probability for being 1. And if your input is 1, it means that the probability for that input is lambda 1. If it is 0, it means that the probability for that input is 1 minus lambda 1. So we finish the first member of our multiplication. Yes? Okay, for the next one. For the next one, how is the parameter for this distribution? It is again a Bernoulli distribution over this random vector with the parameter sigmoid over V2 plus W2 transpose times x less than 2. So I should just generate the parameter for our Bernoulli distribution. I call this parameter lambda 2. And the procedure you see here generate lambda 2. What does it do? The x1 is times the x1 means exactly x vector x less than 2, because less than 2 is just x1. x1 is times W2 and it is added to B2 and then enter the sigmoid nonlinearity and generate a value between 0 and 1, which is the parameter for this Bernoulli distribution. So if your x2 is given to you. If x2 is 1, it means that the resulting probability is lambda 2. If x2 is 0, it means that the probability is 1 minus lambda 2. Okay? So I calculate the second one. Any problem? And I continue this procedure until the end. At the last, how I calculate the parameter for the distribution over the last element, it is easily a Bernoulli random variable over the last element with the parameter generated using sigmoid of B subscript D plus W D transpose X less than D. What is the dimension of WD?
D minus 1.
Exactly, D minus 1. times 1. It's a column vector. And x less than d is also d minus 1. This is a scalar, so the dimension is okay. So I calculate this value, which I call lambda d here, lambda d. Now again, I check if the given xd is 0, it means that this is this probability. If it's 1, if it is 0, 1 minus lambda d is the probability. So I finish all the factors in the chain rule, in my limited chain rule, I mean. So what is the probability of the input? Exactly. I should multiply all of them. And this is how I can estimate the density for a given input. Okay? Any?
For example, if I have an image, yes, when we first start, if I calculate p of x in one order, and then I calculate another p of x in another order.
No. The order is a property of your model. It cannot be changed.
No, I'm asking, in the end, how different will those two models be? Like, how closely are they associated? How different are they?
I think that in that case, it cannot work. Because the model will be trained based on an ordering. It means that you first select your ordering, and then you cannot change it anymore. Yeah. You should use that ordering during all your learning and also inference time. You just have one order. This is some problem with the model of autoregressive exactly for images. For example, in some tasks, as you will see later, for example, you have a uncropping task. It means that a part of a task is valid, a part is missed. Maybe a model trained using this scan can work in this application. But assume that you cannot control your masking process. You are given an image with this mask. Then you start here, and before your information about the image is rich enough, you should estimate a pixel. Here is totally different, the context, you see? This is the missed part, this is the available part, okay? You start here. When you are here, a rich amount of information is in your generative model because it sees the half of the image. But here you just see one half row of the image. And it should start estimating your image or filling the masked values. You know, so there are some problems with applying them in these types of applications, yeah. But you can see, for example, in energy-based model, it is not important how is the mask. It can easily fill any type of mask. Yes, this is the problem with ordering. But as I said, some inputs are ordered in their nature, so it is well defined for those inputs. Any question? Okay, this is the formulation for the previous slide. We define the parameter for Bernoulli random variables given this is the Bernoulli random variable, the Bernoulli parameter for p of xi given x less than I. This is the parameter for this Bernoulli distribution, and as you can see, the parameter is the probability of, if you start using p of theta because you are using a model, and it is not the complete family, so the probability of your random variable be equal to 1 is the Bernoulli parameter, which is the sigmoid over this affine transformation over the previous elements. You define these element, this parameter for Bernoulli distribution, and then, for example, assume that you are given this input. Can you assume that you have access to all of lambda I? Can you fill this distribution for me? So start with the first element. I want P of x1 equal to 0. What is this? You have access to lambda I. Yes. 1 minus lambda 1. 1 because I have calculated those values. So the value for being 0 is 1 minus the Bernoulli parameters. So the next one is the probability of x2 being 1 given x1 is 0. I will write it here because it is given. What is this probability? Assume that the lambda have access to your input. It use the previous one. What is this value? This is lambda 2. Because the probability of being 1 is the parameter of Bernoulli random variable. And continue this procedure. It is not very much here. Given x1 is 0, or I can write it in this form. X less than 3 equals 0 and 1. This is aligned with our notation. What is this probability? Exactly, it's lambda 3. And the last one equal to 0 given the previous one is 1 minus lambda 4. If I multiply all of them, I can calculate the probability of this input using our model. We do not know how the model is trained, but assume that the model is trained. The first element, the second, the third, the last, and the complete. This is exactly what we write here. Okay. Any question about density estimation using autoregressive models? Yes?
Can you do this approach during the training?
We should do it.
Update W and the bias.
You know, here we are estimating the probability of a given x, for example. During the training, what do? You again, because we train based on maximum likelihood, it means that you should calculate this value, for example, for the first training example, as a function of your model parameters. It means v1 till bn d, assume that the dimension is d, and also w less than 2 till w less than d. If you can calculate this as a function of your model parameters, it means that you can increase it. Change the parameters such that the probability for the data you visit in your data set is increased. Yes, density estimation is a crucial role during the training. Yeah, you should do it for several times, and it means that density estimation is important to be fast, because during the training you should estimate the density of all the training data as a function of your model parameters. And it should be very efficient. You will see that in some cases the density estimation is efficient, in some cases the generation is efficient.
So we use this density estimation, I suppose that since we don't know the actual model, so we estimate the probability of each input as an element of the input vector. So how can we update this W and B since we are doing the estimation and we cannot, for example, do back propagation?
Yes.
Do this?
We can do pack propagation. We will see. But one intuition is that a good model is a model that if you sample from your true data distribution, if you sample from the true, how we can sample? We can extract the data set samples and give this sample to your model. You expect this log value should be high. What does it mean? It means that the model is such that for the data coming from the true data distribution, it gives you high values. It's a good point. It means that it is trained such that the data coming from the true data distribution are given high values, and because the volume of a distribution is limited, the volume of a distribution is equal to 1. When you assign high values to data coming from your data set, it means that you are lowering other values at the same time. In other words, you are training the model, or you are learning the true data distribution. Pay attention that you have limited budget. You have a distribution whose volume is equal to 1. If you increase some points, the points coming from the true data distribution, it means that you are at the same time decreasing other points. Points which are not the true data samples, the probability will be decreased. And it is what we want. You can see that maximizing this is equivalent that you are minimizing the KL distance between data distribution and model distribution. It's exactly the same. Yeah. Okay. Any question? I think we should stop here because the next part is the generation based on autoregressive models, and I think we cannot finish it. If you have any question, we can talk. If you have not any question, we can leave it. Thank you very much.